Assalamu alaikum all. Can you hear my voice? Yes, what about others? Okay, so let's start today's session. As I have told you earlier, this week we have two chapters, chapter number 4 and chapter number 5. So chapter number 4 I have discussed in face-to-face lecture, in which we have discussed about SNMP V1 communication, organization and information model. And this is chapter number 5, where we will discuss SNMP V1 communication and functional models. Although SNMP V1 does not formally define a functional model, applications are built in the community-based access policy of SNMP administrative model. But let's have a review of that. Inshallah, we will have it. These are the objectives of this chapter. So here we have SNMP V1 communication protocol, which defines the specification of 4 aspects of SNMP communication. We have architecture, administrative model that defines the data access policy, SNMP protocol, and SNMP MIB. So security in SNMP is managed by defining the community, and only members belonging to same community can communicate with each other. So a manager can belong to multiple communities and can manage multiple domains. So SNMP protocol specifications and messages are presented, and SNMP entities are grouped into SNMP MIB module. So here we have SNMP architecture. This architecture consists of collection of network management stations and network elements, or we can say objects. So here network elements have management agents, and these management agents, they are built inside them. So if they are managed elements, they are built inside. So SNMP communication protocol is used to communicate information between network management stations and management agents. So there are 3 goals of the architecture in the original specification of SNMP. The first goal is that it should minimize the number and the complexity of management functions. And these management functions, they are realized by the management agent. The second goal is it should be flexible for future expansion. And thirdly, the architecture should be independent of architecture and mechanisms of particular hosts and particular gateways. So it should be universal. So only non-aggregate objects, they are communicated using SNMP, and the aggregate objects are communicated as instance of objects. So this has been enhanced in SNMP V2, and SNMP V2 we will discuss inshallah next week, which is given in chapter number 6. And we have consistent with the rest of SNMP standards and ASN 1.1 transfer syntax and BER encoding scheme, which is used for data transfer SNMP. So let's see. the SNMP messages. Now see, SNMP monitors network with 5 messages basically, and they comprise of 3 basic messages, and they are get, set, and trap. So you can see here we have get request, get next request, get response. So this is the get message. Then we have set request, which is the set one, and trap, which includes generic trap, specific trap, and timestamp. So information about the network is obtained by the management stations polling the agents. So the get request and the get next request messages are generated by manager, and these are generated in order to retrieve data from network elements using associated management agents. Now we have set request, and this set request is used to initialize and edit network element parameters. So the get response request is the response from the agent to get and set messages from the manager. The number of messages in the form of trap is limited to make architecture simple and to minimize traffic. Now you can see over here we have 3 types of trap, which are generic trap, specific trap, and timestamp. And these 3 are application specific. The generic trap consists of cold start, warm start, link down, link up, authentication failure, EGP neighbor loss, and enterprises specific. So the specific trap is a specific code, and it is generated even when an enterprise specific trap is not present. An example of this is that we gather statistics whenever a particular event occurs. So such can be used by a particular group. So the timestamp trap is the time elapsed between the last initialization or the reinitialization of the element and the generation of trap. So SNMP messages are exchanged using connectionless UDP transport protocol in order to be consistent with the simplicity of the model and to reduce traffic. So the mechanism of SNMP is suitable for a variety of protocols. Now next we have administrative model. Now let's see the figure. Here we will refer to the application entity residing in the management station as the SNMP manager, and the application entity in the element as the SNMP agent. The pairing of the 2 entities is called SNMP Community, which is given over here. So this SNMP community name is called community, and it is specified by a string of octets. So multiple pairs can belong to same community. Now you can see in this figure that it shows multiple SNMP managers, and they are communicating with a single SNMP agent. So an SNMP manager is monitoring traffic on an element, another manager configuring some administrative information, and the third manager monitoring to perform some statistical study. So we have an analogous situation where a manager communicates with multiple agents. So figure 5.1 shows the authentication scheme, which is a filter module, and it is in the manager and the agent. And the simplest form of authentication is the common community name between the two application entities. Now here we have encryption also, and it is the higher level of authentication, in which case both the source and the receiver knows the common encryption and decryption algorithms. So as you know that in case of encryption, we convert plain text into ciphertext, and in decryption, ciphertext is converted back to plain text. So encryption is done at the sender side and decryption is done at receiver side. So it is important that whichever encryption algorithm we are using at the sender side, the same decryption algorithm should be used at the receiver side. So in this case, both source and receiver should know the common encryption and decryption algorithms. Now, in this figure, we have SNMP Agent, and it has an MIB view of objects 2, 3, and 4, although there may be other objects associated with the network element. So the SNMP authorization is implemented as part of managed object MIB specifications, and a management agent may be permitted to view only a subset of network elements managed object. So in addition to MIB view, each community name is also assigned an SNMP access mode. So you can see the access mode. It can be either read only or read write. So a pairing of SNMP views with an SNMP access code is called community profile. So a community profile is basically combination with the access mode of a managed object, which determines the operation that can be performed on the object by an agent. So for example, in this figure, you can see that an SNMP agent with read-write SNMP access mode can perform all operations, get, set, and trap on objects 2, 3, and 4. And if the SNMP agent has read-only access mode privilege, then it can only perform get and trap operations on object 2, 3, and 4. So object 1 has a non-accessible access mode, and hence no operation can be performed on it. So we have SNMP and non-SNMP communities, which are managed by SNMP manager. And the practical example of it is that we have a network of LAN and WAN, and LAN could be a TCP/IP network with SNMP agent, and WAN could be any network like X.25, which is not an internet model, but can be managed via Proxy Agent and integrated into overall management system. Now we have access policy, where we have peer processes which implement SNMP, and therefore it support SNMP application entities, and they are termed as protocol entities. So communication among protocol entities is accomplished using messages which are encapsulated in a UDP datagram. UDP is User Datagram Protocol. So an SNMP message consists of a version identifier, an SNMP community name, and a protocol data unit, that is PDU. So here we have a manager which manages community 1 and 2 network components, and it is through Agent 1 and Agent 2. Agent 1 has only view of community profile 1, for example Cisco components. Agent 2 has only view of community profile 2, for example 3Com components. It is the name of vendor, 3Com. And manager has total view of both Cisco and 3Com components. This is the generalized administrative model, where manager 1 manages community 1 and manager 2 manages community 2, and manager 3, which is the manager of managers, it manages both community 1 and community 2. Here we have proxy access policy, where we have SNMP manager of community 1, and under SNMP manager we have SNMP agent and proxy agent. And SNMP agent is responsible for SNMP community and proxy agent is responsible for non-SNMP community. So basically proxy agent enables non-SNMP community elements to be managed by an SNMP manager, and SNMP MIB is created to handle non-SNMP objects. Now here we have encapsulated SNMP messages, and the version and the community names are added to the data PDU, that is protocol data unit, and along with application header is passed on to the transport layer on SNMP PDU. The UDP header is added at the transport layer, and which then forms the transport PDU for the network layer. The addition of IP header to the transport PDU forms the network PDU for the data link layer, that is DLC. And the network or DLC header is added before the frame is transmitted onto the physical medium. So you can see here, initially it is an SNMP PDU which consists of only data. Application PDU consists of application header, version, community SNMP. Then transport layer consists of UDP header and application PDU. Network PDU consists of IP header and transport PDU, and data link PDU consists of DLC header and network PDU. So an SNMP protocol entity is received on the host except for trap, which is received on another port. Now, these messages, they are encapsulated and then they are transmitted. Now here we have get and set PDU. So PDUs are supported in all implementations, whether we have get request PDU or we have get next request PDU or get response PDU, or we have set request PDU and trap PDU. So one of these 5 data PDUs is the data PDU that we start with at the top. And RFC 1157 SNMP macro definition can be given through this. Now, in this figure 5.8, we have conceptual presentation. So we have get and set type PDUs. This is just a conceptual presentation. Now, PDU type for 5 messages are the application data types, and they are get request, get next request, set request, get response, and trap. So in this figure, you can see we have request ID, and it is used to track a message with the expected response or for loss of a message. Because what we are using UDP, User Datagram Protocol. And User Datagram Protocol, you all know that it is an unreliable protocol. Can you tell me why? Why it is an unreliable protocol? And can you tell me which protocol is reliable one? Good. TCP is a reliable protocol. And why UDP is unreliable? Because it is private? No. It has no acknowledgement. Yes, because it is connectionless. Because it is connectionless protocol. TCP is reliable because it is connection-oriented protocol, right? It is connectionless. So we have loss of message detection, and it is implementation specific, such as timeout if no response is received for a request within a given time. So we have a non-zero error status. Here we have an error status. So a non-zero error status is used to indicate that the error has occurred. So if it is 0, that means, if it is 0, what does it mean? If error status is 0, yes. If error status is 0, what does it mean? And if it is non-zero, then what does it indicate? Get request. We are talking about error. If error status is suppose 1, what does it mean? It means that the error has occurred. If error status is non-zero, if it is 1, that means the error has occurred. And if it is 0, that means there is no error. Okay. Now here in this so generally this is the case that we are using, that if it is 0, then that means there is no error. But if it is not 0, if it is any other value, then we say that there is an error. But here in this convention, we do not use 0 if no error is detected. Okay. Here in this convention, we don't use 0 if there is no error. Okay. We will discuss later on how we will find out if there is no error, what value we have to give later on. So you have to remember in this case. Now next is we have error index. And this error index is used to provide additional information on the error status. So the value is filled with null in those cases where it is not applicable, such as in get request data PDU. Otherwise, it is filled with VARBIND. Okay, means variable bind number, and where the error has occurred. For example, 1 if the error occurred in the first variable bind, and 5 if the 5th variable bind had an error, and so on. So this figure shows the structure of trap PDU, which contains n variable binds. You can see over here we have variable bind 1, n, and so on. That is, we have n managed objects. Okay, n managed objects. Now the enterprise and the agent address, it is pertaining to the system which is generating trap. So the generic trap consists of 7 types, as you can see in this table. There are 7 generic trap types. The integer in the parenthesis is associated with each name, and it indicates the integer value. Now the specific trap is a trap that is not covered by enterprise specific trap. So the time stamp indicates the elapsed time since last reinitialization. So here we have cold start 0, which means that sending protocol entity is reinitializing itself. Agent configuration or protocol entity implementation may be altered. Then we have warm start 1, which means sending protocol entity is reinitializing itself. Then we have link down, link up, authentication failure, EGP, neighbor loss, and enterprise specific. Now here we have SNMP operations, which comprise of get and set messages. and these are from the manager to the agent. And get and trap messages are from agent to manager. So if we are talking about messages from manager to agent, we have which type of messages? If the messages are from manager to agent, which type of messages we have? We have get and set messages. Get and set messages from manager to agent. Get and set messages. And if we are talking about we have different categories of get requests, get messages. Okay. So get request is one of them. So when we are talking about SNMP operations from manager to agent, which type of messages we have? We have get and set messages. And when we are talking about SNMP operations from agent to manager, which type of messages we have? Get and trap messages. Note it down, get and trap messages. Okay. Very important point, note it down. Now here you can see in this figure, we have sequence of operations in retrieving the values of objects in a system group. So it starts with get request operation using get request PDU from a manager process to an agent process, and the get response from the agent with a get response PDU. So the message from the manager it starts from the left side and ends at the agent process on the right side of the figure. Now the messages from the agent process it starts on the right side and ends at the manager process on the left side of the figure. So the sequence of directed messages moves with time, and as we move down the figure, now messages depicted represent the values of the 7 objects in the system group. The manager process starts the sequence with a get request PDU for the system object. The agent process returns a get response PDU with a value Sun OS. And the manager then sends a request for system object ID, and it receives the value which is not clear in this figure. It's E:HP. So the exchange of messages goes on until the value of 72 for the last object in the group sys services is received. So this is get request operation for system group. Now this is the MIB for get next request. So get next request operation is very much similar to the GET request, except that the requested record is the next one to the object identifier which is specified in the request. Now here, the first two objects, A and B, they are single valued scalar objects, and they are followed by an aggregate object which is represented by table T with an entry E, and two rows of three columnar objects, that is T dot E dot 1.1 through T dot E dot 3.2. So if we are talking about this, how you are going to name it? How you are going to name it? How you are going to name it? T dot E dot 1 dot, this is, we will name it T dot E dot 1 dot 1. Yes. Now what about this? What about this? What about this? How you will name it? No, it will be T dot E dot 3.2. Okay, 3.2. Now see, in this MIB group, which is the last scalar object? Which is the last scalar object? Yes, we take the last number, Z. Yes, Z is the last scalar object. So how many scalar objects are there? How many scalar objects? Yes, there are 4 scalar objects. We have A, B, T and Z. Okay. But if we talk about T, this is what? This is what? It has sub branches also. So it will be called as aggregate object. In addition to scalar object, it is also called aggregate object. And T represents table and E represents entry. So if we will categorize, we have 3 scalar objects, we have 1 aggregate object, and this object is represented by T, which means table, and it has entry which is represented by E. This is clear? Now see this one more time. Okay. See, this is the MIB for the get next request. Here we have first 2 objects. These first two objects are A and B. As you can see, this is A and this is B. First two objects. These two objects, they are single valued scalar objects. Single valued. And what about last one? It is also single valued scalar object. Okay? Single valued scalar object. Now, you can also say that this object is also a scalar, but because here we have sub branches, so we will categorize it in another category. So instead of saying that T is a scalar object, we will say that it is an aggregate object, because here we have sub branches. So in general, what we have three scalar objects and we have one aggregate object. Now this aggregate object is represented by T. T means table, and under T we have E. What does E mean? E means entries. Clear now? Okay. So now here we have a table which shows lexicographic order number example. Here we have procedure for ordering. It starts with the leftmost digit as first position. Now, in order to explain this, there is one more figure, but it's not given in this slide. And it's important to discuss that figure first in order to understand this lexicographic order. Okay, let's discuss. See, the left side of this shows the sequence of numerically increasing integer numbers. So we have 1, 2, 3, 9. It's in increasing order. And the right side is lexicographically increasing order for this sequence. So we have 1, 1, 1, 1, 8, 1, 1, 5, and so on. So we can notice that in lexicographic order, we start with the lowest integer in the leftmost character, which is in our case is 1. So before increasing the order in the first position, we select the lowest integer in the second position from the left. Which is 1, 1. So there are two numbers. We have 1118 and 115 that starts with 1, 1. Now we anchor at 11 for the first two positions, and then we move on to select the lowest digit in the third position, which is 1, 1, 1. And then we move to the fourth position and we will obtain 1118 as the second number. So now we return to the third position and we retrieve 115 as the third number in the row. So we have 1 in position 2, 2, 4 and select 2 for the second position and then retrieve 126 as the next number, and we continue this process again and again until we reach 9. So we will apply the lexicographic sequence to order object identifiers in MIB. So instead of each character being treated as a literal, we treat each node position as a literal, and we follow the same rule. Now in this, the MIB associated with this is shown in this figure. This is the MIB for operation example. It can be noticed that the lexicographically increasing order of the node traces the traversal of the tree starting from the leftmost node. And the leftmost node is 1 in this case. Now we traverse down the path all the way to the leftmost leaf, and it is 1.1.5, the leftmost leaf. Now we will keep to the right until a fork is encountered. We then move up the tree and take the right on the first fork, and then we get 1.1.18. Now this rule at the fork node is to always keep to the right while traversing down and while going up. So we are always keeping to the right if you imagine ourselves walking along the tree path and looking in the forward direction. So we turn around when we reach a leaf. Leaf is what? The end node, which has no child node. That is called leaf. So returning to the get next request operation, the get response message contains the value of next lexicographic object value in each variable bind. So we have discussed until slide number 20. This is slide number 20, and you have 4 more slides, but we have no time now. So please go through it and the concepts that we have discussed in today's lecture. And if you have any question, you can ask in face-to-face lecture or virtual lecture or in the office hours. Till then, take care all of you. Assalamu alaikum.